All right. Thanks for the invitation from Rebecca. I'm going to not talk too much about differential privacy because even though I do work on differential privacy, but I want to talk a little bit about some work I've been doing with people in particular in computational neuroimaging, trying to. Well, actually, my part of the project is to bring try out some differentially private algorithms there, but this is more about context, I guess. So the kind of systems I've been working on are sort of collaborative research systems, which is a bit different than the data sharing that we heard about earlier today. These are things like secondary use of clinical data for research, which means that you have data that's been collected in the hospital already, and you'd like to open that up to researchers, perhaps at your own institution or at other institutions, but not sort of to the public. Things like running multi-site studies on sort of I don't want to call it meta health, but like things like quality assurance or comparative effectiveness research, which is again on sort of already collected data within in the clinical setting. And the thing I'd like to talk about a little bit today is on joint or sort of secondary analysis on research data. So the model that I always talk about is, we have a bunch of research groups who are studying, say, schizophrenia, and they've all taken MRIs, and they'd like to do some joint analysis across these MRIs, even though each group might be studying something completely different about the disease. So, the overall abstract picture is that you have these institutions that want to share data, and sort of the status quo, at least in neuroimaging, has been for a while that you have this scenario. People have the same kind of measurements. They might not have been asking the same kind of questions, but they have the same kind of measurements. They'd like to do a joint analysis on those measurements. And of course, the data sharing, as we heard this morning, often could require lawyers at each institution. So you could have sort of this pairwise lawyer interaction graph where you negotiate out, hammer out who's allowed to use the data for what. And of course, this, as the number of nodes increases, this becomes sort of impossible even for moderate scale collaborations. So, the sort of solution thus far are kind of to create research consortia, which, it's kind of like a club, usually around different conditions such as Alzheimer's or autism or breast cancer, for example, depending on what you're actually studying. And so then you'll have these groups in this consortium, and they'll sort of agree to collaborate. But what that collaboration form takes is not necessarily fixed, and in particular, not necessarily thinking about the computational aspects of it, which is, I guess, what I'm interested in. And so automated sharing, or sort of like having, our data is accessible on our servers, and you can get information from the data that's on my server just by running some query. That's changing. I mean, that's becoming more and more feasible. So the idea is, well, what can we do with that sort of thing? And so, in particular, offering some kind of privacy protections, and they need not be as strong or as formal as differential privacy, can actually encourage people to join consortia and sort of be willing to share access to their data. So my collaborators have this system already called COINS, which they call COINS, which is for managing brain imaging studies. So these numbers are now, I don't know, increase them by a certain amount from, say, December to now. They have, tens of thousands of participants in different scan sessions and a lot of from a lot of different locations. And this system is sort of, partnered with existing research consortia. In particular, there's one on autism. I think there's also one on addiction. So the goal is to kind of extend this. So this is just like data warehousing. There's no computation really going on here. So we'd like to essentially run some analyses on data that's sitting, that's the metadata is organized by this coin system. So, like I said, for example, as an algorithm, as a sort of machine learning guy, I'm like, okay, I'd like to train a classifier that can like take in an MRI, a structural MRI, and then give a label as to whether that person has schizophrenia, right? It's a pie in the sky kind of thing. And so what we have are these MRIs from multiple studies. So you have multiple studies with healthy controls and people with schizophrenia. And in particular, I'm assuming away all of the kind of registration and sort of getting the data in the right format, assuming it's all in the same format. And then we can just run our, if I had all the data in one place, I could just run support vector machine or something on this, and I could do it. But we're not actually allowed to aggregate the data in one place because that would require signing all these data use agreements. So can we essentially run a distributed computation? To run a distributed computation, everybody computes some aggregate, perhaps with some epsilon for differential privacy, and then there's some kind of aggregator that'll put it all together. And the answer is yes. So we can build systems that look like that. We can build algorithms that look like that. And the advantage of doing something like this is that everybody gets to keep control of their own data. And they're just answering questions. They're answering questions about their local data set, and then we can control the leakage through, they can control their own leakage through say, differential privacy or any other method they choose. So how does that model compare to sort of what exists now? And what exists now is this actually really great system called Enigma. Where MA stands for Meta-Analysis. Oops, I didn't get to finish this sentence. So it's the Enigma system, which you can go to this URL to take a look, has a pretty broad goal to understand brain structure and using genomics and imaging and genetic data. So. The kinds of validation they've been doing is that they say things like they've been looking a lot at neurophysiological measurements. So there's like what is the volume of the hippocampus and how does that vary across the population? How does that vary with certain genetic markers and so on? So those are the kind of questions that they're answering. It's very interesting stuff. But how would that work in the context of say doing a linear regression, right? So I'll get to that in a second. So but they have there's a lot of interest in the community, right? They already have 30 working groups, which are organized under the aegis of this Enigma study. But in order to say do a regression analysis, you'll write a proposal to the people who manage the system. They'll say, okay, this looks good. This satisfies all our rules. That's a moderately slow process, but not like super bad. It's like the IRB. And then what happens is they say to each of the participants, okay, go run your analysis and email me an Excel spreadsheet with your regression coefficients and a bunch of other things. And you get this emails of Excel spreadsheets. And then somebody, probably, I don't know, probably not a graduate student, but has to sit there and kind of line up these Excel spreadsheets manually, right? And what's great is that it works. You can get some nice results out, but it's pretty slow, right? Because this is all being done by email and Excel. So this manual meta-analysis. So the low-hanging fruit here is, of course, can we just automate this process by putting it on a server or something like that? So CoinStack is a system which tries to do that, right? Basically, once the data is registered in coins, then we avoid the Excel channel and do it automatically, through some centralized.
Never mind. Also, this secures the data you're trying to.
Yeah. There's a lot of benefit, right? Yeah. So the communication's encrypted. All sorts of things are better. As I said, but this is low-hanging fruit. So, again, we have the slow process of proposing a study or a particular thing that you'd like to do. And then you have to have this, again, kind of slow process where somebody at your, my lab says, sure, you can use my data for this. And then everything works automatically. So that's great. Obviously, this can be significantly faster because it avoids the Excel issue. So again, so these ad hoc so basically the way things are defined in the system is, you define these consortia. Either they can be ongoing, so I'm going to run multiple analyses through one consortium, or I'm going to sort of on an ad hoc basis say, hey guys, can you let me have access to your data? And then basically once you have a consortium, you can initiate these kind of joint analyses. And then we do some message passing between the different servers. The data is always staying at the different labs, so there's some message passing that happens to implement the whatever algorithm, whatever analysis you'd like to do, and then it spits out an answer. So where does it stand right now? We have a demoable thing, like we can go to the NIH and be like, look, it's working. Sort of. But it's not really up and running, with a lot of participants at the moment. That's sort of going to happen in the next year. The goals sort of in the medium term we'd like to do is, right now we can do things like summary statistics, or we can compute ridge regressions and simple stuff, the stuff that we were doing with Excel. So we'd like to be able to show that there's a value add beyond avoiding Excel. In particular, things that I don't know that much about, which is, surprising stuff that I'm learning, is, things about the user interface and the usability. It's in order to get people to use a system like this, you really need to have good visualization tools. And it's unclear how sort of visualization methods and differential privacy, for example, could work together. It seems like since you're producing a rather low-dimensional aggregate, it should be good for that. But I, haven't seen that. That's an open area for work. And we're going to, partnering with people who work on certain types of addiction to as a sort of prototype for the real run of this kind of system. And in particular, now the way things are set up right now, it's very easy to test, a differentially private method for doing something, computing some function of interest in the system. So that's actually pretty good. And my student Hafiz is working on this sort of thing in the back. You can ask him about it. So because the focus of this kind of system, this is speaking a bit to Adam's, researcher practitioner divide. This is also kind of this algorithm designer and algorithm user divide. Because we're trying to focus on the usability for this particular research community, we are basically not doing a lot of innovation in the methods department in terms of the actual methods, because we want to show them that they can use the methods that they want to use. In particular, things like independent component analysis or independent vector analysis or non-negative matrix factorization. Of course, everybody wants to do deep learning, so we're going to have to do some deep learning. You're not doing machine learning if you're not doing deep learning now. So things like regression and classification. So these are methods which I can think of as maybe being more along the lines of feature discovery. And in fact, feature discovery in this area is particularly important because you want to have interpretable features. That says that this brain region is active in this under for people with this condition. And then, as I said before, visualization is pretty important, and so there's a group of people working on visualization. So now to take a step back, because I said this, I was asked to talk about sort of health research, right? This is a very particular solution for a very particular sort of research community, right? This is a focus. And this works for this sort of neuroimaging research problems. So is this a big data problem? So people ask to say, oh, you're working on big data. And I said, well, the data is big for neuroimaging people. Like, this is a lot bigger sample size than people are used to doing. And so this big is big from the perspective of the domain area. It's not big, it's not terabytes. I'm not processing terabytes of data here, maybe in the future. Big is in the eye of the beholder. And particularly other things that happen in this scenario is that methods which have asymptotic guarantees are not ideal. In fact, may not work at all. So, your favorite streaming algorithm, which looks really good because it's sublinear, is not going to be the thing that you want to use here. So, it's I don't like hacking around, but this kind of gets close to the border of you gonna kind of hack around until you get something that works. So there's a question of what principled things can we do here. And in the sort of strong formal privacy guarantees end up getting kind of trumped by utility requirements because the sample size is sort of small with respect to this statistical sense. So we sort of lack, at least, and that's because oftentimes the utility guarantees that you get are also asymptotic for these methods, even for differentially private methods. So, to get good utility, you need large sample size. So that's sad news. Maybe like no privacy, at least from the perspective of formal privacy measures, is good enough. So in particular, from the regulatory standpoint, essentially just making sure the data doesn't go to another party seems to be good enough for a lot of people to sign off on starting to use this system. So it's enough to kind of build a system like that for now. And in fact, getting these algorithms to work on the kind of computing infrastructure that we have is actually challenging, which I'll talk about in a second. And the other thing that's different about sort of data sharing to the public is that the threat model feels different. So the question is, what can we say meaningfully about sort of this controlled environment where I know who's making queries and I know a lot about the system? How should we think about those kind of scenarios, which is, again, different from this public sharing? And I think this is actually fairly common, that is, these kind of scenarios are fairly common in healthcare research. It's not a lot of it's less of a push to open source or open data, a lot of healthcare data. But on the other hand, I think it does provide a useful test case for looking at differential privacy or things like other people work on multi-party computation in these kind of settings. So I think it's good to have a setting where you can try these things out, right? So as I said, a challenge for using differential privacy is that, as Adam pointed out, mentioned, differential privacy involves introducing some randomization. In particular, we often think about it as noise, but it doesn't have to be noise, as he said. But if I do think about noise, if you have a small number of subjects, which is typically the case for these kind of studies, I mean, the number of people in these schizophrenia studies is quite small. You end up introducing a larger amount of noise for a fix to guarantee a reasonable privacy, and so you'll get privacy risks, so you'll get a lot of error. Another challenge that's particular to neuroimaging, but also I think in general for a lot of imaging and this kind of data, is very high dimensional, and so to get methods to work properly, you need some reasonable dimension reduction methods, or you need to, again, figure out how to handle that with differential privacy. And from talking to people who want to build these systems, there's a real preference for these stronger epsilon zero guarantees, but all the kind of improved analyses that I know about in terms of composition and so on rely on sort of allowing yourself a little slack of delta in the privacy definition, and that I've been told by at least a few people that, oh no, that's not okay for our application. So what do you do there? The other big challenge has nothing to do with privacy in particular, although it's coming from this sort of heuristic privacy constraint. If I don't want to put the data, where other people can actually get it, is using cloud services is not really okay for many of these applications. So this forces everything to be done locally. So this local storage overhead, it can be challenging. Maybe not for a research group because the data sets are not too huge, but for hospitals or healthcare centers, that can be quite a lot. And also the local processing costs are heterogeneous. So that is to say, the computation time I need and the computational resources that I need can be quite different. And the final thing is that communication now is not communication within a data center. So which communication within a data center is pretty fast. I can have threads talk to each other and so on. Now I have to, it's back to kind of midway between Excel and a data center. Like, I still have to pass messages between groups. And if I'm passing, say, a gradient, a 50,000 dimension gradient every iteration, and I need to run for 1,000 iterations, that's a lot of communication overhead, and I'm subject to network latency and stuff like that. So this actually has kind of killed an initial implementation that we had. So we're making a lot of compromises, I guess is the point I'm trying to make, and we'd like to make fewer compromises. I think that's kind of the research goal, is to make fewer compromises. In particular, the first one is we're making utility first. So make utility great again. We're going to practical values of epsilon for differential privacy are going to be large in this setting, and we'd like to figure out how to get them to be reasonable, like the 1/10 that Adam mentioned. And instead of looking at these iterative methods, iterative methods are great. Gradient descent is great. Stochastic gradient descent is good. But if we have to do it with communication between nodes, it's bad. So we have to figure out how some intermediate between this one-shot aggregation and iterative methods. So right now we're living in the kind of one-shot aggregation model. And then the other thing is to stick with simple tasks. That is, I would like to go and design new methods for really cool matrix factorization methods that will do some really cool stuff. But in fact, you need to stick with methods. We need to stick with methods that have buy-in from the practitioners first. And I think that was maybe it's obvious to everybody else, but it wasn't so obvious to me at the beginning. I thought we could do everything all at once. So the other thing is that data sharing in general in these healthcare research is, as I said before multiple times in this talk, is different than open sharing or this industry academia sharing, and that's because there are a lot of different. The regulatory framework around personal health information is different, so therefore what's allowed and what people think of as being allowable is different. There's this informed consent model in healthcare research, which potentially can allow for each individual to have their own privacy preference and allow certain types of sharing and certain other their data to be used at that level of granularity, which is can be tricky to manage. And this was brought up in the morning. Data sharing could also be contingent on the task, or it could be transient. The data could not be available tomorrow. And so sharing the data or sharing a version of the data is, and by version it's a little bit, I put in air quotes, may not fly. Okay, so just to recap, I guess the shared access models with privacy protections, whether they're formal or not, we do encourage people to join research consortia. We've had some interest in people who were not previously involved in Enigma to join to look at interested in the CoinStack system as a solution. The reason that they were not interested in Enigma as much is because they thought it was a little slow for them. But I mean, that or they hadn't heard of it. So. The benefits, the nice thing in this setting that I've looked at, I think, which is different than some other scenarios, is that the benefits and risks kind of align with the desires of the data holders. This is not the case in certain types of healthcare research where either people are very risk averse or they're very benefit hungry and care less about the risk. So here things kind of line up well. People are we can sort of please them on both sides. In particular, these data holders can retain control over their access and what computations are allowed, so they feel like they're in control of the data that they have. Whereas the users of the data could hopefully in the future, will be able to do pretty complex hypothesis generation in a fairly automated way that will lead to really some new interesting results. So some lessons learned, again, just to recap, it's good to start small. It's quite challenging to bridge this gap between maybe the researcher and the practitioner, but in this case, in building systems, the algorithm designer and the software developer. It's also quite tricky. And the communication requirements in these kind of methods, that is in terms of network communication, are non-trivial. And that was a surprise because I don't think of that as necessarily being a big deal for the types of computation we were looking at. Just to bring up a couple of other things that are not related at all to this neuroimaging context. One is this iDash Center. So who here has heard of the iDash Center one? Obviously, okay. There was a talk about it earlier, right? So it's yeah. So it's a Center for Data Sharing at UC San Diego, and they're working on sort of larger scale secondary use of clinical data. So they want to make this clinical data warehouse that they have more accessible and useful for researchers. So that's the objective. And the range of problems is very diverse and like not at all like this. I mean, not at all in the sense that it's not. I've been focusing very much on this in this talk on imaging, but the problems in data compression. Questions on GWAS type questions, natural language processing, and all of these questions come with privacy challenges. And they're very good at issuing data challenges. They have a lot of internships, so they do try to transition some of that research into more practice. And I think maybe this is a good model for how to get some of the research methods into practice. But I just emphasize the features of these problems are very different from each other. So there's a large, very wide range of problems. I'm going to skip that because I'm just in the interest of time. Because so how do we sort of this data hub? How do we move this forward with respect to sort of healthcare type research? And I think the first thing is that I got asked to give a talk about medical and healthcare data, and really that's just like it's almost meaningless in terms of actually thinking about the data and the type of problems. Like there's such a wide range. You have to. I can talk about the one little thing that I know a bit about. But we have to, so we really need to spend some time delineating the problem space and figuring out where, what are these different systems? A research thing is different than a comparative effectiveness research. So we need to spend some time thinking about these, and then from that, I think more interesting problems will pop out. And so, the theory question I think is sort of the most pressing on my end is, can we figure out how to get out of these sort of asymptotic regimes, and can we actually figure out what's going on in the finite sample setting in a way that speaks to the kinds of data that we have in this setting. In particular, if you think about this data, it's data about individuals. Your sample size is at least upper bounded by, let's say if you're doing work in the US, the number of people in the US, right? So that's an upper bound on your sample size. So what can we do there? It's not search logs, right? It's not search log level sample sizes. And then the thing I found challenging in talking to the practitioners, and this is the way that I've been trying to approach it now, is trying to figure out what people want to do. Like, I want to compute a regression, versus how you want to do it, which is I will have all of the data and then I will be able to do whatever I want. And so being able to specify these tasks, which is what then we want to implement in our system, that's the challenge. And so I think if we can solve this and then build methods that kind of work well in the settings that we have, we'll do pretty well. And so that's all I had to say. So thank you. Yeah.
Hi. Do you know the Odyssey consortium?
No.
So there are probably a lot of lessons to be shared between the two. So Odyssey is something like 140 researchers in 20 countries, federated approach with a common data model, a mock data model.
And what setting?
Observational health data.
Oh, observational health data.
And it encompasses something like 600 million patient records, and the way that it operates, I had to pull it up because I'm not an expert on it, but I think it addresses some of the challenges that you're having. So people join the collaborative, they propose a study, they write a protocol for it, they code it locally, post on GitHub, publish it, and then folks, they execute it in their own data set on the common data model, and then they aggregate the results centrally. So
do they rely on people to run the execution manually, essentially?
Yes, that's one of the challenges, right? There's not, the automation is still lacking there. but it does solve kind of the aggregation problem where, and the propagation of what you're trying to do and what you're proposing to do. And it also allows people to decide whether they want to do it.
Right, so it's, yeah, very, very simple.
And it's, you don't mind my adding on, since I'm an active member of that.
So much more of an expert than I am.
Well, yeah, but I have experience with it. It's of a type that there's about 3 really large within the U.S. similar types that are predicated on a common data model, a federated system where you pull on your data.
Yeah.
And things are generally run locally and aggregated, but not always. There might be disagreements otherwise. But you mentioned UCSD, so there's one of the sites that bridges 2 of those 3 very large national networks is partly centralized at UCSD. So I was wondering, though I had not heard of that, they developed an application called Scanner that was meant to facilitate certain classes of analyses. Is that?
Yeah, well, I don't know if iDash is in charge of Scanner, but the people overlap.
So Danielle Meeker and some of those same.
Yeah, I think they're involved. So.
Is it the implication much larger than expected? Like, what are the...
Well, it's like it was slow because, it's slow because I would normally, it's like it's going over the network from New York to say Albuquerque, and it's just the gradients are big, and they're kind of sitting there, going back and forth and like waiting for latency things, and it's like the latency was.
So what is bad for you? Like, is 1 day of the sort of back and forth latency?
No, so that's
bad, or is 2 hours bad? Or?
Well, so that's the thing. It depends on what you want to be able to do. If I want to be able to sit around and kind of muck around with the data until I find something, then I want something fast. But if it, for a lot of things, it's like set up the experiment, hit go, come back in the next morning, and it's done. Then that's fine, and that would work. But if you're also at the same time trying to do parameter sweep or something like that, then you have to run it multiple times.
You're not shipping like gigabytes.
No, it's not. No, it's more of a latency issue than like aggregate network traffic. Yeah.
So actually, I'm not sure I quite understood the model for the private computation. Sorry, is the idea that with the Excel spreadsheets, all the data was still collected in one place?
Well, no, I'd send you regression coefficients, right? I send you my W in an Excel spreadsheet.
Okay, I see. So the idea here is that you still really want to avoid this central aggregation point, and in this particular context for these types of computations, people look at multi-party computation protocols, the other things you mentioned.
Yeah, so the hard part about for the kind of tasks that we want to do, we'd like to do things linear algebra on real numbers, and doing linear algebra in multi-party computation right now with current multi-party computation techniques seems a bit challenging. Sluggish. You have to do a lot of multiplies, which seems to be so people are interested in it. That would be a great solution, but it's like not at the plug and play level. Whereas sort of adding Laplace noise to something is definitely at the plug and play level in terms of testing things out.
Well, that's kind of a nice branch to our next talk about multi-party computation.